Welcome, everybody, to Weekly Quantum World Detangled, Season 1, Episode 9. This week, we have a truly global superstar guest, Rodney van Meter, calling us from Japan, Keio University. Afterwards, Denise will share some business news about Honeywell and other fun stuff from the last week. Tommaso is going to talk about his paper of the week on quantum certification and benchmarking. And we're looking to pick Rod's brain on predictions of the future of quantum computing. As always, I'm joined by my friend Denise.
Hi, everyone. Denise Ruffner, Cambridge Quantum Computing, coming to you from sunny Pasadena, California. And
hi, everyone. Good morning. Tommaso from Entropica, calling you from Singapore. Today, again, very rainy, beautiful monsoon period. And Rod?
Hi, I'm Rod Van Meter. I'm a professor at Keio University's Shonan Fujisawa campus in Fujisawa, Japan, south of Tokyo. And the weather here has been monsoon weather too, but today I managed to bike to campus. I'm back in the campus about 1 day a week right now.
Awesome to have you. My name is André, König, CEO of Interference Advisor. Rodney, how did you end up in Japan? It's one of my top countries on my travel to-do list. Never been always to go. How did you end up there?
It's a long story. I was working at Information Sciences Institute, the ISI, which is part of the University of Southern California, back in the 80s and early 90s, and I was doing some work that originally was very interesting and got transferred to a project that wasn't very interesting. And I had friends who were working for a small company here in Japan, and they said, we're looking for engineers. I said, okay, I'll come. So I came for a few years and then went back to the United States for a few years. But I had heard the name Keio University while I was here. And one of the professors here at Keio is a guy named Jun Murai, who is now in the Internet Hall of Fame. He's one of the people who brought the internet to all of Asia. He's the guy who brought it to Japan through a group that's called the WIDE Project. And so I've known about Keio for a long time and known it's a good place. I was looking for a place to get a PhD in quantum computing, and I wound up coming to Keio and coming back to Japan to do my PhD. I was planning on going back to the United States after finishing a PhD here. My wife and I wanted to spend a few years here in Japan, but we weren't planning on settling down. But Keio's Shonan Fujisawa campus called and offered me a spot as a tenure track faculty, and 14 years later, I'm still here. So everything's great.
My biggest Japanese success story, which turned out my failure, was me trying my hand at the ninjutsu, the art of the ninja. I've done martial arts all of my life. And that was with supposedly a very famous teacher from Japan while I lived in New York in his early 90s who didn't speak a word of English and had a nice little bamboo stock. And the first 3 months of class, all he did is correct the alignment of my toes because he didn't like how my toes were pointing. And I eventually gave up and did not become a ninja. Do you have any secrets to success on striving in Japan for the last 14 years?
Well, no, not in particular. I was never one of these people who was really sort of longing to go to Japan. It was just more or less coincidence that I wound up here, and then I'm actually comfortable. And there are a number of things that I do here that are sort of Japan related, you might say, or Japan focused. Like I'm a Go player, although I don't get to play very often. But other than that, my life is pretty suburban. I commute to the office and I go to my daughter's track meets, and that's pretty much my life.
We look forward to hearing more about your adventures and your thinking out of Japan. Let's look at the business news.
everyone, well, it's here. Finally, Thursday evening, we started to see press on the Honeywell 64 quantum volume quantum computer. Very exciting. At the same time, there was a paper published on Archive by the JP Morgan Chase Group, Marco Pistoia and team, working with this computer and raving about the quantum volume. So it's a new day in the quantum computing world. I think this is the first of many advances, and I'm really excited to see what the future brings for both Honeywell, as well as IBM, as well as Rigetti and all the other players. But today we have a new lead in town, and that's Honeywell. And so I encourage all of you to read about it. I'll post the archive paper, which has gotten some good play on LinkedIn. And I just encourage you to learn more about the Honeywell device, and reach out to me if you want to hear how CQC has used the device. We were one of the beta testers. So it's an exciting new time with new technology.
What did you learn using the Honeywell device when you did at Cambridge?
Very interesting. We were worried that the trapped ion was very slow. And what we found out is that while we might normally do 9,000 shots or do a lot of shots on a calculation, we had to do considerably less. So between 500 and 1,000. So actually we needed less compute time than we thought. So it was interesting because we had signed up for a lot of compute time thinking we needed it. And we made it through all our experiments very quickly because we needed less time. And the accuracy is amazing. So it's our team is quite excited about using it. And we're actually going to be filming a journalist come and watching how something runs on a Honeywell quantum computer. So that should be fun.
I haven't had a chance to look at this at all yet. What do you know about the software tools for it?
So the software tools, so right now it runs on QuizKit, or you can use the CQC kind of middleware called Ticket, which is a compiler level software that also has mid-circuit measurements, which is a nice feature.
So they're supporting feed forward on this already?
Yes.
Ooh, outstanding. Now there's a feature.
Yeah.
Good. Exciting news indeed. We had Tony Utley from Honeywell on a Weekly Quantum World Detangled 3 weeks ago, and we'll keep updating everybody as we learn more. Let's look at the science paper of the week.
Sure. Did you prepare yourself this time?
Test me.
Okay, you should be able to see my screen, hopefully.
It's coming. Yep.
Okay, technical reviews, Nature. Paper is called Quantum Certification and Benchmarking, came out just a few days ago. Really impressive list of authors. What I love about the paper is that it's very pragmatic in spirit. As the title suggests, it speaks about certification and benchmarking. So maybe, André, I can ask you, you know the difference between the two?
Between certification and benchmarking?
Yes, is a subtle one.
Benchmarking is the comparison between different variables. So certification is the observation of one.
Maybe we can try to be a bit more precise in the statement. Specifically for quantum computing, one of the features of quantum computers is that we believe they are going to be more powerful than classical computers. That is fantastic, but it also becomes an issue because we have ideas, but one of the practical problems that we are going to face when quantum computers scale up is that it's going to be hard, or at least it's not going to be trivial to test the correctness of the computations that they are performing, right? Because you cannot use a classical computer to check if the computation is correct indeed because of, the whole issue and blessing of quantum advantage. And this is really what quantum certification tries to capture. How do you certify the correctness? How do you verify if a quantum computer is working as it should or not? Well, benchmarking says something more. It says something about the performances of the machine. So you could speak about gate benchmarking, or you should maybe look at you could start thinking, although it's a bit premature maybe, about benchmarking with respect to specific application of a quantum computer and so forth. So this is really, if you like, the difference in a nutshell. And what this paper does, which is great, they So first of all, in this figure 1, I'm not sure if you can see it well. Let me zoom a little bit. They share, or they list a number of techniques, and they plot them against assumptions and more or less information gain. So you can get a sense of, like, you need less assumptions and you can gain more information, or vice versa. This figure doesn't say anything about the complexity of the techniques. So some of those are very hard to do in practice. It's just telling you something about the features of those techniques. But then if you go down, if you scroll to page 4, and this is great, for anyone who's looking at actually getting their hands dirty, there is a one-page table with a list of certification, characterization, and benchmarking protocols, which is very comprehensive. And furthermore, I think they did something which is very impressive. Scroll down to page 7, and I'll show you another page. They give you a link to an online certification library, which I'm going to open now here. They don't have a protocol for all of the techniques that they state in the paper, but some of them do. So for example, you could go and have a look at quantum gate set tomography. They speak about the assumptions, notation, Arduino requirements, etc. This is really great, right? So we are starting to see more comprehensive effort and really make sure that we understand how the machines are performing, that we have a, I would say, well-accepted, or a set of well-accepted methods to benchmark these quantum computers, which is something that I personally really love. So I hope people will find the paper as interesting as I did.
It is. So what do you think it takes, and I'm asking more about the approach rather than the metric, to really assess the performance of a quantum computer? And in the beginning, it was all about qubits, right? Then
Sure.
IBM came up with the quantum volume. Now that Google and Honeywell are doing really well at quantum volume, IBM is talking about circuits. Today, actually, Japan announced a new supercomputer that's 2.8 times as powerful as the previous supercomputer. What does it take, you think, to really assess the performance?
This is a really good question. It's also very hard to answer. I can give my take. I would love to hear Rod's thoughts on this as well. So I think all the benchmarks, if you like quantum volume, number of qubits, these are all fair games. Quantum volume, I guess, is an okay one to move forward. I mean, now Honeywell seems to be embracing it as the figure of merit. I don't know if it's nuanced enough to actually really tell the whole story. I personally don't believe it is, but that's fine. I think for now, though, we still have to really think in terms of different platforms and still make fair comparisons between the different machines. For example, Denise was speaking about the time that it takes to run a computation on a trap ion machine. And as far as I know, a quantum volume really doesn't capture that. But it's important for people to know that this is is a difference, for example, between the IBM machine and the Honeywell machine, or even the future PsiQuantum machine. So the short answer to a difficult question is that there's a lot to say about benchmark, and I don't think we still have, and maybe we will never going to have a single, number, if you like, for that. Rod, do you have anything to add?
I don't have anything in particular on the choice of metric there, quantum volume versus other things. One of the things that we have used goes back to a paper by Andrew Steen, who's one of the key ion trap people historically, a paper of his from the 1990s, where he talked about what we call the KQ metric, where Q is the number of qubits you're using in your circuit, and K is the circuit depth, and you just multiply the two of them. It's actually related to IBM's quantum volume, but the calculation method's a little bit different. It's actually, in some ways, a little bit of a simpler metric, I think. So we've found that useful for talking about how complex an individual circuit or an individual problem is, and then the question is, how do you match that to a machine, and what is the probability you're actually going to succeed? Eventually, I think there will be a metric on the order of dollars per solution for a problem, and you'll be comparing quantum machines versus classical machines. But we are a very long ways from something like that. I do have a couple of other comments, though, on this. One, this paper has been floating around in draft form for, I guess, about a year. It was on the archive before it was actually published. I haven't looked at the published form, but it looks like it's actually grown quite a bit. But it's a fantastic paper. I completely agree. It's going to be one of the benchmark papers for a while, I would think. But there's one aspect that's actually slightly different for a case we care about a lot. Most quantum researchers are trying to figure out how to benchmark or evaluate systems as the size of the system grows. As we get to 50 qubits, 100 qubits, how are we going to characterize this system? We also do a lot of work on quantum internet, quantum repeater-based systems. And so we're doing a lot of design and evaluation work there. And what we care about for that is not how you're going to characterize entangled states with large numbers of qubits, but instead how quickly can you characterize small quantum states with just a little bit of entanglement. Because in a quantum network, making entanglement between two places is actually an extremely expensive operation. So for example, that paper, one of the tables you were scrolling by talks about O of how many operations is it going to take to run a particular characterization benchmark. As an engineer, of course, I love that O of notation, but it also hides a constant factor. And for a lot of these algorithms you're talking about, that constant factor might be 3,000 or 5,000 or 9,000 or something in order to collect enough data to run the statistical measures that you're doing for calculating that. That's okay in a system in which you can get 5,000 or 9,000 shots in a few seconds of runtime on a particular quantum processor, but in a quantum network that generates 10 entangled states per second, 9,000 states for your characterization protocol is a long time. So that's one of the problems we're working on, and we've actually been talking to some of the authors of that paper about this particular problem.
A very complex topic, and as the business person and investor, customers moving into quantum computing, laymen like us, we obviously need some metric that we can hold on to that allows us to assess what folks are doing. So as long as we have nothing better than quantum volume or potentially circuits, I think that's a great metric for us to look at. Tommaso, do you want to start with some questions for Rod?
Yeah, for sure. I would love to. So, Rod, again, thanks for joining us. It's always a pleasure.
I'm happy to be here. I really am. Thank you all for inviting me.
So I'll be honest. I love reading your blog. It's always a great source of inspiration. And I remember from a few months ago, I think it was February, you had a post called "The Science Fiction Short Story About Quantum Computing" or something very close to that, where you were making predictions about what is going to happen in the next 10 years or so in the field of quantum computing. I loved it. It was great. I thought it was very down to earth, very pragmatic, which is good. So maybe one question that I have using that as a little bit of inspiration is the following. Do you think there is something today in the whole discussion about quantum computing, especially with commercialization getting closer, or at least it seems it's getting closer? Do you think there is something that people are not discussing, either purposely or not, that they very well should? It's like, is there something that we are all swiping under the carpet, pretending is not a problem, but it actually is a big problem, or at least is something missing from the conversation?
I think the single biggest item that we haven't yet really addressed in terms of the performance of systems is how we're going to deal with problems with big data. People talk about, well, we can use machines for quantum AI, or maybe we can solve large graph problems using these systems or something like that. That remains the single biggest Achilles heel of the systems that are being designed and implemented today. So you can do a system that uses a small number of qubits but has a very complex algorithm, what we call a branching factor that grows very quickly. So sort of a canonical example would be something like chess or shogi or Go, one of those board game problems where the amount of state you have to represent something is not very large, but there are lots of possible next moves, and so the total possible number of games grows very quickly. It doesn't take a lot of data, but the computation itself actually grows extremely quickly in terms of the total complexity. Now, as it happens, there are pretty good heuristics for solving those problems, and they have a certain structure. So those problems themselves might not be the ones that get implemented as some of the first really commercial applications for quantum computers. But that's kind of the way you want to think today, is what kind of problem has a small state representation but a really complex computational space as it grows. So that's great, but it's going to ultimately limit what we can really do with the systems. And instead, what we would like to do eventually is we would like to be able to work with very large data sets, a large graph structure, or a lot of images if you want to do image recognition, or a lot of language databases if you want to do automatic translation, or whatever it is you want to do. A lot of the most important problems in the world today really require a lot of data. And at the moment, we don't have really good ideas for how you can bring those data into a quantum computer. Denise, you were going to say something?
Yeah, I was going to ask you where you think the first solutions are going to be, given the number of qubits, given what you were just saying, that there's a small number of qubits and you have to be careful on what problems you solve and you address, and the amount of data you can put in. Where do you see the first solutions coming from?
Where will the first real commercial applications for systems be? Is that kind of the question?
Yes, sorry. Yes.
I would say it's probably going to be in the quantum chemistry space. That's sort of a trite answer almost these days, and everybody who's in the field knows that was actually one of the first things that Richard Feynman actually proposed as an application for quantum computers when he was writing some of the original idea papers that became sort of the seed for our entire field. Quantum chemistry involving the bonding of atoms into molecules, they have a large number of potential states for the electrons in such a system. They can be in different energy states. The atoms can be in different physical configurations, how far apart the atoms are, what the angles are between the bonds, what modes they're vibrating in. All of this determines the amount of energy that's actually in a particular molecule. And that's one of the things that's actually very complex to calculate in a classical fashion. And it's believed to be those are the kinds of problems that a quantum computer can actually solve fairly well. I'm not actually an expert in this area, although I actually have co-authored one paper on quantum chemistry with James Whitfield, who was a student of Alanis Buruguzic's at Harvard at the time. My contribution to that was to figure out how we can get the computer to do the arithmetic that's necessary in their algorithms. I'm not really a quantum chemistry expert, so I can't really point you to specific problems and say this exactly is a problem that we think will be one of the first ones that will be solved. But that broad area of chemistry and material science seems like maybe the most attractive area for near-term actual use. The idea that a quantum computer might calculate something for us that we can't actually calculate classically.
So this is very interesting, actually. And now, since you're speaking about big data, and you mentioned quantum machine learning and how to transfer classical information into a quantum computer, or at least part of it, that immediately makes me think of QRAM, of like a quantum random access memory kind of system. So if I remember correctly, in that blog post I mentioned before, you predicted that we would have the first experimental realization or prototype, I don't remember the exact words that you use, for a QRAM in 2028.
Yeah, you know why I said 2028? I just needed to fill a particular gap in the timeline I was creating.
That's fine.
I said this is a science fiction story. It's literally just science fiction. All right, let me guess what might happen over the next 10 or 15 years. The next couple of years, we can see pretty clearly what people are working on. But then after that, then you get into the range of, well, we know we're going to need breakthroughs.
Right.
But yes, so quantum RAM is a good one. It's the one really serious idea for how we might deal with large data types in it. And the basic idea there is that you have some device that's storing a substantial amount of classical information, and each data element that's being stored in it has some sort of a key, an address that you use to access that particular thing. Then you have to have a device that allows you to create a complete superposition of all of those addresses or keys and give that to the database, and then get back a superposition of everything that comes out of it. And Seth Lloyd from MIT has been working on that. There's actually sort of the core of the idea in the original Mike and Ike textbook that everybody uses, Nielsen and Chuang's book. There's the core of the idea there. But as far as I know, nobody's really working on what you would consider to be practical implementations of that. And it's something we're going to need. I've called it the $1 billion patent. If you had a good way to do that today, IBM or Google or somebody would pay you $1 billion for that patent. That might be an exaggeration, but it would certainly be a real game changer for the entire field, not just for individual applications.
Yeah, I mean, I agree with that. I also find it quite interesting that there is not, at least openly, people are not really looking at that. Or there is not like a startup looking at building a quantum RAM, which honestly would make a lot of sense. So maybe this is an idea for somebody who's listening out there now. But what do you think then of quantum machine learning? Because quantum machine learning, in a way, kind of relies, unless we're speaking about the kind of problems that you mentioned at the beginning, or unless we're speaking about very specific problems that have a small data sets, et cetera, what of quantum machine learning? If QRAM is not anywhere near, and quantum computers don't have enough, cannot handle with enough coherence to actually prepare the state that we need directly, what of it?
So one of the things we do need in conjunction with the development of the hardware ideas for the QRAM is we need more advances in how those will actually get used in algorithms.
Right. Yeah.
One of the areas where people have sort of written frameworks for algorithms, this is sort of a common thing in computer science theory papers, is you write what's essentially a framework for an algorithm, and you have this function in your framework for it, and you say, you just sort of assert, well, magic happens over there. As long, given the access to this kind of magic, then we build an algorithm around that magic, and that ability to get in these large superpositions is one of those kinds of things. Machine learning and quantum computing in general, people like to put together the buzzwords because they're both sort of common, really popular buzzwords these days, really exciting buzzwords. There are actually a couple of ways in which you can put those together. One of them is quantum machine learning, where you're talking about running classical problems or solving specific problems on a quantum computer using a quantum algorithm that helps you with some machine learning tasks. The other side of it is you can do machine learning for quantum computing. So you can use machine learning to help you design a quantum computer or help you compile programs effectively for a quantum computer. Or one area where it's actually getting quite a bit of attention goes back to the paper you were talking about. So Jens Eisert's paper on quantum certification and benchmarking. A number of the techniques that people are looking at for those are essentially machine learning based techniques for actually evaluating the machines themselves. So I think both combinations are particularly attractive, but the quantum machine learning, I think, will remain sort of small problems which could mostly be solved classically fairly straightforwardly until we can find some way to actually deal with relatively large data sets, or find real algorithmic advances that help us create better hybrid algorithms, where part of the algorithm is classical and part of the algorithm is quantum. Hybrid algorithms, if you just define it that way, all of the quantum algorithms, they're all hybrid algorithms. Shor's algorithm involves a certain amount of computation before you start classically, and then you do the quantum part. There's a certain amount of classical stuff again after you do the quantum part. But when people talk about a hybrid algorithm, what they really mean is something that's adaptive or that uses feed forward inside the system, where you do a little bit of quantum stuff and then a little bit of classical and a little bit of quantum and a little bit of classical. So there may be ways to take some of these problems and break them down into smaller subproblems and get those subproblems to be solved on quantum computers. That's a really active area of algorithmic research. And I don't know if you saw on one, was it on that blog post or a different one? Peter McMahon pointed out to me a couple of earlier papers on essentially the ideas of hybrid algorithms. And the ideas actually go back to the 90s, although a lot of the most exciting and interesting work has really been in the last 5 to 10 years.
One question about software development in quantum computing, since we were kind of touching on it just before. Do you think we as a community have even started to actually develop software for quantum computing, software with capital S, or we just still tinkering about with, trying what these machines can do and see what happens?
That's actually an excellent question, and I meant to circle back around to that when we were talking earlier, and we didn't get back around to that. Today, the software that we're developing, a few hundred lines of Python, a few hundred lines of Qiskit is considered to be a pretty good-sized program, and it's not very hard to write a program today that exceeds the capability of today's hardware to execute it with any sort of fidelity at all, and to write a program that exceeds our ability to simulate these things. But in the next decade or two, we're going to be building large-scale systems, and we're going to have to find ways to build large-scale software systems for this as well. What happens when we get to software systems for quantum computers that are 10,000 lines of code, 100,000 lines of code, a million lines of code even? We don't have the tools for doing that. We don't have the tools for building the intuition in young programmers to help them learn how these things work. We don't have the tools for helping advanced developers test the behavior of small parts of their system and then reason from those to how the larger system will work. And we don't have the ability to debug quantum programs at any sort of useful level. All of those are areas that are ripe for a tremendous amount of research. There's a lot of work going on quantum programming languages. Qiskit and a lot of the others really work at sort of the gate level. They're operating at low-level logic operations, the equivalent of and or gates from the classical logic that we all learned in our first computing class or our first logic class. What are the high-level structures, the high-level things that you need to think about, to reason about large-scale programs and large-scale software systems? And we don't have that yet. I actually have a PhD student, a woman named Sarah Metwali, who's actually, her PhD thesis will be in this area. What's it going to be like to program large-scale quantum software systems over the next couple of decades? So it's not only an area I think it's important, it's an area we're actually putting effort into.
I'd like to ask you the opposite question that Tommaso kicked you off with when he wanted to know if you believe we're missing something in the field. Is there something, and you've been very pragmatic in your answers, which the German in me appreciates and enjoys, is there something in the industry that you are very excited about that people might not be talking about? Do you see an opportunity that might be really life-changing, game-changing, that you are excited about?
Ooh, that's a really good question. That's a really good question. What is it that I'm most excited about at the moment? Wow. There are lots of things to be excited in the field as a whole. One of the areas we're actually doing quite a bit of work in is trying to understand how we can use the near-term machines, what we call the NISQ machines, a term that nobody's used yet today, those near-term machines for actually solving problems in graph theory. I think that's an area where there's a lot of potential for quantum computers to actually contribute. But that's also an area with a tremendous amount of classical work behind it. There's a lot of theory and a lot of people who've worked on those ideas and on how to deal with very large graphs and large data structures for decades. So I think it's exciting, but there's still quite a ways to go before it sort of surpasses classical machines in that sense. What else would I consider to be sort of the exciting things about this? I will tell you that Keio has hooked up with IBM. We're a member of IBM's Q network, and so we have access to the top end superconducting systems from IBM, and we have a number of industrial companies who've come in to partner with us on that. And you might think, well, given the state of the machines and the fact that they could all be more or less simulated, give or take the arguments with Google and IBM, why would you need access to a machine right now? But I'll tell you, since we've had access to the machines, the rate of our own learning has really just accelerated and advanced in ways that are really hard to describe. So internally, it's been a huge boon for us, but it's also been really a positive thing for attracting students and collaborators for us as well. So just the advances in the hardware in and of themselves, I think, are creating a lot of excitement.
As always, we could be talking for a couple hours. We do need to put an end to it. Arigato gozaimasu, Rodney. Pleasure having you all the way from Keio University. We have a new website, quantumworlddetangled.com. Check it out. This was season 1, episode 9 of the weekly Quantum World Detangled. You are now detangled.
Mm-hmm.